Okay, so after that kind of quick introduction to vectors, now let's meet their companion, which is known as a one-form. So the way I'm going to go about defining one-forms is taking the kind of abstract algebra perspective, in that essentially, well, we think of vectors as living in a vector space, and now this is just a set of objects. We could consider another set of objects, which is going to be a set of maps. And now what we're going to want to construct is the set of all maps from this real vector space into its kind of underlying real space. And what we're going to realise is that when we construct this set of all maps, we're going to realise that that set by itself also has a vector space structure. So we take all of the possible maps that we could possibly have into R. These are linear maps. I'll start giving them some names. Just by linear map, I simply mean that we can add the two maps together and they can act on sums about elements in V. And now essentially we collect this set of all linear maps of V into R, and as a whole set it forms a new object which is known as the dual space, or the dual vector space, and we give it the name V star. So the way to kind of formally state this is that we realise V star as essentially being the set of all maps from our set V into R. And now another thing which we can then go on to realise is that given V star, well, we could consider what's the dual of the dual space, and we can go round and about and realise that, well, the dual of the dual space is going to be isomorphic to the actual vector space, blah blah blah. And essentially we boil down to the realisation that dual vectors are linear maps from vectors into real numbers, but you can just work this the other way around and realise that vectors are linear maps from dual vectors into the real numbers. So you can equally define a vector space as being a space of all linear maps from some dual space into the real numbers. And now what I mean by these spaces being spaces of linear maps, essentially each of the individual maps behaves like a vector in that we can add them together and they can act on two vectors being added together, and we can also scalar multiply the maps and so on. If you want to see all of the details, I've made more detailed videos covering these two topics. So we're going to expect now that a one form is going to be something which lives in this dual space. It's going to be something which takes a vector and just maps it into a real number. So that's simply how we're going to define a one form. For now, we're going to just define it, and then we're going to really see what it kind of is and what it does. So I've written some here. A one form, let's for now call it omega. It's going to be a map that takes a vector into a real number, and this we essentially write by saying we take any vector v and we map it to this object omega v, which is a real number. So I've just defined an arbitrary map from a vector to a real number, and I'm calling this a one form. So this is all just, haven't really done anything significant yet. All I've done is just written down what a linear map is from a vector. But this is now going to be a one form, so we're going to realise it's going to live in a dual space. And now this dual space, it is simply just a vector space. It's going to have its own basis, known as the dual basis. So what we're going to see is that one forms, just like vectors, are going to be able to be expressed using a basis. And now we're going to see there's going to be some kind of differences to how we place our indices. But for now, I'm going to index my components using a lower index, and my basis using an upper index. Remember when we wrote down the vector basis, it was this E new object, well, now we're going to see that the dual vector basis is this E with an upper index. And now I just want to say that this placement of indices, upper and lower, is a completely arbitrary conventional choice. We could have chosen to say, have our vector basis index be the upper index. It doesn't matter which way round they go as long as we're consistent once we've made the choice. So the convention is that vectors bases have lower indices and dual bases have upper indices. And now this gets really, really confusing when you hear physicists talking about vector and dual vector indices, because what physicists are talking about are the indices on the components. If the basis has a lower index, we know that this means we need an upper index on the components in order for the sum convention to work. And now you'll hear a physicist referring to this V mu as a set of vector components with quote-unquote vector indices. Whilst this is kind of true, these are vector components and this is a vector index, these are actually really just real numbers. The only vector part of it is this actual basis element, which has a lower index. So, no, this is just my opinion, really, these should be the vectors, or the vector indices, and these should be the dual vector indices. But it's just how we have to deal with things, because physicists always ignore the basis and they only talk about components. Okay, so that was just a bit of an aside on conventions. You'll sometimes also hear these referred to as covariant, contravariant. That's all nonsense. Just think of them as being vectors and dual vectors. So I've begun writing here. This is our expansion of the one form in a basis. So remember, the one form as an object is kind of a higher object than the coordinates we're using. This is just, remember, these bases are going to come from some coordinate system, and this expression here is essentially now the way this one form is kind of realised in coordinates. As an object, this omega is a more abstract kind of linear map, but we can give it a concrete representation using components. And this representation using components gets even more concrete when we choose a particular basis, known as the coordinate basis. So I introduced you to the kind of vector coordinate basis in the last video. We saw that it was given by these partial derivative operators, which essentially take the coordinate, or it will take in any function and it will just give a infinitesimal vector pointing along the direction that that function is increasing in a particular coordinate direction. So remember, this d mu is the derivative with respect to some particular coordinate, and that's essentially just going to give you a little vector pointing in the direction of this coordinate. And so we're going to have something similar for our one form basis, and I'm just going to simply tell you it's given by the following object. So this new thing which I've introduced, this dx mu, is what's known as the one form coordinate basis. And now how should we understand and think about this object dx mu? Well, this d, which I've written here, does have a concrete definition. It's known as the exterior derivative. So I've made other videos covering the exterior derivative in much more detail. Just really briefly now, I'm going to tell you that what the exterior derivative does is it takes now not necessarily a one form, n, what's known as an n form, that could be a zero form, a one form, two form, and so on, and it takes the derivative of that n form and it produces an n plus one form. So I'm just going to tell you now, we define zero forms to be just simply functions. So this x mu is just the coordinate functions. It's just a zero form. So taking the exterior derivative of, and now this is just some notation, we usually denote the space of forms using a kind of omega, and then we have a number up here that represents whether it's a, and then the number here represents the rank, whether it's a 1 form or a 0 form, and so on. So the exterior derivative takes an n form to an n plus 1 form. That's just how it's defined, but how it actually acts, so how we simply just define the action of the exterior derivative on a 0 form is that, well, we've seen it has to produce a 1 form, so it's going to give us some set of components, and then we're going to just again have the 1 form basis. So this is how the exterior derivative is simply defined, and now we can understand what dx mu is if we just simply plug into the definition. F is now not x mu but just x nu, so if we just say dx nu, this is going to be dx nu by dx mu, and then again our 1 form basis dx mu. Okay, now this might look a little bit trivial, but essentially, so this dx mu is essentially now just going to give us a Kronecker delta. And so we're just going to have delta mu dx mu, which is just then dx nu. So this is just the definition. It does feel slightly circular, but we should really just understand what this dx mu object is the definition of the exterior derivative acting on a 0 form, our coordinate functions, and it gives us this kind of object df. We're going to see a little bit more now in the next video what df kind of represents as a 1 form. What's essentially now going to happen is that this df is going to have to be kind of fed into a vector in order to produce anything meaningful. This kind of dx mu, you can simply just define it algebraically, having structure on its own as just simply an object. You can just take this as the definition. So we're going to see in the next video a nice way to kind of interpret these dx mu objects using kind of infinitesimal distances. We're going to see that when we realise that dual vectors are dual to vectors, or that 1 forms, are dual to vectors, what we're going to realise is that when we take a 1 form and let it act on a vector, it's going to produce something which is going to give us a nice intuitive understanding of what dx and what these basis vectors kind of represent. But that'll be coming in the next video. For now, this is just how we simply define 1 forms algebraically, and how we define this kind of new dx object using the exterior derivative of our coordinate functions. And so I just briefly commented about the conventions that we use for our components. We always say that our 1 form components have lower indices, and then to remember, there's some convention, our basis has to have an upper index, and then likewise with vectors, vector components have upper indices and their bases have lower indices.